It's Paul with an R script that's designed to illustrate some important ideas about infinite sequences, namely Cauchy sequences and increasing and decreasing sequences. So let's make a sequence named Cauchy. I've defined this sequence by a function of an integer n, so that conceptually there are an infinite number of terms. But for displaying it, I want to make a vector. So I will make a vector of the first 100 terms of this sequence and plot it. If you look at it, you see that this sequence tends upward. It also wiggles a bit, and on looking at it, you might guess correctly, as it turns out, that the limit is 1. If you look at the function that defines the sequence and see that n plus 3 in the denominator, you can see eventually the term that's subtracted from 1 is going to go to 0, so the limit really is 1. But we're not trying to show that this sequence converges to 1. We're trying to show that it's a so-called Cauchy sequence, and here's how we do it. We pick an epsilon. I pick 0.14. And now, for reasons that will become apparent in an instant, I choose n equals 7. Now, look at the terms of the sequence to the right of the blue line, the terms beyond the 7th term. I can construct a band of width epsilon going from 0.88 to 1.02. And no two terms beyond the 7th term, no two terms to the right of the blue line can differ by more than epsilon, because each pair of terms is trapped in that band. Notice that the limit of the sequence was irrelevant to constructing this band. To say that the sequence is a Cauchy sequence is to say that I can always do this, no matter how small an epsilon I choose. But first, notice that this first band alone sets an upper bound and a lower bound on the sequence. It can never go above the top red line. It can never go below the bottom red line. So we've already proved that every Cauchy sequence is bounded. Now let's go with a smaller epsilon, 0.07. After a little fiddling around, I discovered that n equals 17 was a good choice to go with this epsilon. Why? Because if I consider only terms beyond the 17th term, the difference between any two of them has to be less than epsilon, for the simple reason that all those terms lie in the band between the dotted red lines. One more example. With the still smaller epsilon of 0.03, I choose n equals 53. And now I've got a band that runs from 0.97 to 1 within which all the rest of the terms lie. Notice the top edges of my band keep coming down, and the limit of the sequence is equal to the least upper bound of the top edge of the bands. If you look at the bottom edges of the bands, they go up, and the limit of the sequence is also the greatest lower bound of the bottom edge of the bands. Now remember, for real numbers, by the completeness axiom, every sequence of real numbers that's bounded above has the least upper bound. Every sequence that's bounded below has a greatest lower bound, and therefore these two quantities are guaranteed to exist if we have a sequence of real numbers. That's why a Cauchy sequence of real numbers always converges. Couple more points about these bands. First, we didn't need to know the limit to set up the bands. That's why Cauchy sequences are useful. You can show that a sequence is Cauchy without knowing what its limit is. Then, knowing that it's Cauchy, you can assert that it's convergent. Also, these bands are nested. Each one lies inside its predecessors. The top of a band can never go below 1 because this sequence has a limit of 1, and there are terms arbitrarily close to 1 which would rule out any greater lowest bound that was anything less than 1. Now let's think about what would happen if we tried to show the sequence was convergent directly. In that case, we need to know that the limit is 1. I've specified an epsilon of 0.03 again, and what I need to do is set up a pair of green lines on either side of the limit. If you look to the right of the green vertical line, you'll see that all the remaining terms lie in between the top and bottom green bands. Now for our next topic, a rather difficult one, the limit superior and limit inferior, known to those familiar with them as the lim sup and lim inf of a sequence. Our family used to own a West Highland Terrier named Zippity, and she loved to dig. So let's imagine we've got a terrier that digs a hole every day. Some days she feels lazy and doesn't dig the deepest hole that she's capable of, though. When she starts out, she's full of youthful enthusiasm and digs really large holes, but as she grows up, her excavation potential stabilizes. The biggest hole she can dig goes down, while she becomes more disciplined, so the smallest hole that she can dig gradually increases in size. So here is a function named terrier that captures this idea. 2 is the sort of standard hole, but onto that I add a random number that can range from down near minus 0.2 up to 4 over n greater than 2. Let's generate 300 values of this to make a vector, and let's plot the first 200 of them. Now there's a series that certainly doesn't have a limit, and the reason is that this terrier is erratic. The size of the hole dug every day is a random number. However, although this sequence does not have a limit, it has a lim inf and a lim sup. Following the approach in the textbook, I'm going to look for dominant elements, ones that will never be surpassed. It took me a while to figure out how to express this in R, and you don't have to worry about that. Just look at the plots of the dominant elements. I've now put them in red. And the characteristic of a dominant element is you look at one of them and say, that's the biggest hole that Zippity is ever going to dig. That is, every time we pass one of these dominant elements, the supremum of the rest of the sequence becomes less than it was before. And while the sequence doesn't approach a limit, this supremum approaches a limit of 2, which I've shown in red there. That's because when I consider a specific dominant term, precisely because that's a dominant term, I can say all the remaining elements of the sequence are less than 2 plus epsilon. And notice they can be a whole lot less than 2 plus epsilon. When you're talking about the lim sup of a sequence, you're only worrying about the amount by which terms in the sequence might exceed that. Now we can do the same thing with the smallest hole that Zippity digs. Borrowing some terminology from music, I'm going to use subdominant as the opposite of dominant. And let's find the subdominant elements and plot them in green. There they are. Every time we pass one of these subdominant elements, the infimum of the rest of the sequence goes up. Or to put it in doggy terms, we say, Zippity's maturing. Never again will she dig a hole that's that small. And this infimum, as you can see, approaches a limit of 1.8. What exactly does that mean? It means that when we go beyond a specific subdominant term, shown by the dotted green lines, all the remaining holes are going to be larger than the one that was dug that day. Now we have come up with a remarkably simple proof of the so-called Bolzano-Weierstrass theorem for a bounded sequence. With any sequence that's bounded, there are two possibilities. The first possibility, illustrated in the graph, is that there are infinitely many dominant elements. And since a dominant element is larger than any of its successors, these have to form a decreasing subsequence. If there are infinitely many, they form a decreasing subsequence that has infinitely many terms, and furthermore, it's bounded below because the sequence is bounded, and it therefore converges. Suppose there aren't infinitely many dominant elements. Well, in that case, there's a last one, and we just go beyond the last one. Since there are no more dominant elements, we can just keep picking terms, each of which is as large as its predecessor. That gives us an increasing sequence, not necessarily strictly increasing, but nonetheless increasing. So we have a bounded increasing sequence, and that converges. So that's the proof of the Bolzano-Weierstrass theorem. Given any bounded sequence, by looking at the dominant elements, either you can find a decreasing subsequence or you can construct an increasing subsequence. In either case, that sequence converges, and we've proved that every bounded sequence contains a convergent subsequence.